Now that we've introduced the idea of nuclear energy, let's try to understand what radioactivity is a little bit better. All right, so what is radioactivity? The definition there, the spontaneous emission of radiation by certain elements. This was coined by Marie Curie. So what's really cool about Marie Curie is she's a woman who was a scientist who was actually given credit for her work. So you'll hear her mentioned a lot in different things, especially with radioactivity. She did a lot of really good work, a lot of really dangerous work too, to the detriment of her own health. But, as a woman myself, and seeing just kind of how dominated the scientific world was by men, it's really cool to actually see a woman get credit for the work that she did. All right, so we have several different types of radiation. Here are the three main ones that we're going to look at right now: alpha, beta, and gamma. So alpha, again, is that helium nucleus. All right, we have two protons and two neutrons, which is why our mass number is 4. And so what happens is when we emit an alpha particle, our daughter nuclide will have a mass number that has decreased by 4 and an atomic number that decreases by 2. Now, a beta particle is basically an electron, right? And so our mass number is not going to change, but our atomic number will increase by 1 because of that -1 on the electron. And then gamma ray, it's just a photon, very high energy, very dangerous, but we're not going to get a change in either the mass number or the atomic number. All right, so our alpha particle, again, we are emitting a helium nucleus. So an alpha particle, again, is just a helium nucleus. We bounce that out. So here's some uranium-238. That's our parent nuclide. And we emit out that daughter nuclide of a helium nucleus, and then we get uranium-234. So 238 minus 4 gives me 234. 92 minus 2 gives me 92. So again, the 90 and the 2 are going to add up to 92. So my atomic number on the bottom stays the same. 234 plus 4 gives me that 238. And so we get that balance there for our nuclear reaction. All right, so a periodic table is going to be really handy for this. We're going to try a couple. All right, we've got some plutonium-238. We're going to lose an alpha particle. We want to write the nuclear reaction. Okay, so we get this 239. Now plutonium, when I look on the periodic table, it has an atomic number of 94. So we'll get that. All right, we're going to emit off an alpha particle. All right, and so 239 minus 4 gives me 235. 94 minus 2 gives me 92. And when I look on the periodic table, what's element 92? It's uranium. And so there's my completed reaction. Okay, radium-226, we're going to get alpha emission. So we'll get, okay, when I look on the periodic table, radium is element 88. All right, we'll get our alpha particle. All right, 226 minus 4 is going to give me 222. 88 minus 2 is going to give me 86. So I look on the periodic table, and element 86 has a symbol of Rn. Okay, so that's how we write our alpha decay. All right, our beta particle. So basically what's happening in beta emission is a neutron is going to split into a positron and a proton and an electron. This gets spit out as a beta particle, all right? And so you can see here, I have lead-210 and I get bismuth-210. So 210 plus 0 gives me 210. Okay, and then I have 82 down there, so I need to balance on the other side. So 83 plus -1 gives me 82. So those numbers do balance down there. Okay, so my little picture covers up part of this. So my carbon 14. Okay, so we're going to get that electron. So the 14 isn't going to change, but I've got that -1 there, so I need to get that. So we'll get that nitrogen there. Okay. All right, let's try this one. So radium-226 is going to decay by our beta emission. Or radium-228. 226 is our alpha particle. Radium-228 does our beta emission. Okay, so now look on the periodic table. We're going to get this 228 still. All right, we need to go up by 1. So before I write it, look on a periodic table and see if you can figure out what element 89 is. You should get that. Okay, and then our gamma emission. So we get energy. So something is unstable. It'll put an M sometimes next to it to stand for metastable. Sometimes there will be brackets around it. There's a few different ways of writing it. But here I've got some technetium-99. Well, it needs to get rid of that excess energy. So we still have technetium-99, and it just emits that gamma radiation there. Now, one interesting thing is that a lot of times we get a lot of energy with these reactions, right? And so sometimes we get not just gamma decay, but we get alpha decay with that gamma emission. So uranium-233, we get this kind of decay. So we're going to get uranium-233. Would really be helpful if I did not write it backwards. That's better. All right, so I'm going to get that gamma particle. Okay, I'm also going to do my alpha particle. All right, so 233 minus 4 is going to give me 229. 92 minus 2 is going to give me 90. And I'll look on the periodic table, and I get that. Okay, so again, when we balance our nuclear reactions, it's a matter of balancing our mass numbers and our atomic numbers, not the number of atoms on each side. Right? So I mentioned that band of nuclear stability. So basically, we can do a plot here, and we can figure out what we have for stable isotopes. We get the Z to N ratio, and that's our number of neutrons to number of protons. And so 1-to-1 doesn't work for the whole periodic table. So you can see there I've got a line for a 1-to-1 ratio, but what we see on the stability zone is we see it differ off of that. And so as we get further down the periodic table, as we get to heavier and heavier elements, we end up needing more and more neutrons per each proton to help keep everything stable. Okay. And so what'll happen is a lot of times something will decay until it gets to something stable. And so uranium-238, it goes through 14 different decay steps until we get down to something that's stable. Lead-206 is stable. It will end this decay series. So we get a series of alpha and beta decays until we get down to something stable. And again, we can predict what type of decay we expect to see based on our neutron to proton ratio, and knowing about where it is on the periodic table and what ratio we're looking for. We're not actually going to calculate that. If you were taking a more in-depth chemistry course, this is actually something that I go over in a second semester chemistry course. I actually do make my students predict the type of decay various different nuclides will undergo. But I just want you to understand that there is a ratio of protons to neutrons that we need in order to have something that's stable. And when we're out of that ratio, we decay until we get to something that is stable. Now, one interesting thing is that what we get with these radioactive nuclides is we get something called a half-life. So we get the amount of time required for the activity or the sample to decrease by half. And so we get this symbol T sub 1/2. So every single radioisotope has its own half-life. Plutonium-239, very long half-life, but plutonium-231 has a very quick half-life. So we use these things in all sorts of different applications. Carbon dating, so carbon-14. Carbon-14 is radioactive, okay? There is carbon-14 that exists naturally, but it's a teeny tiny amount. And so we can actually look at the half-life of carbon-14, and then we can look at a sample of something and figure out how much carbon-14 it has. compared to how much carbon-14 a living creature has and figure out how old something is based on it. It has a limitation based on the half-life of carbon-14, but we can date things that way. There's other things like we'll use radioisotopes to put tracers when we do certain kinds of medical scans. And so for those, we use radioisotopes that have very quick half-lives, things that'll last long enough to do our scans, but not so long that it hangs around in your body forever. Half-life is exponential, and so you can see it goes down in a curve like that instead of a linear fashion. So we can look and we can actually do some fancy calculations, and we can actually do some very easy calculations, understanding that each half-life we just divide in half. So I have a half-life of a sample of 4 hours, which means it takes 4 hours for the activity to drop by half. So 1,000 to 500 takes 4 hours. 500 to 250, that's another half, takes another 4 hours. And 250 to 125 takes another 4 hours. So we've divided in half 3 times. So how many half-lives is this? 3. Okay, so what's our total time that it takes to go from 1,000 DPM to 125 DPM? Well, I've done 3 half-lives times 4 hours each, so I'm going to get 12 hours. So it takes a total of 12 hours to decrease that sample down to 125. Now, the other important thing is that we go from 100%, so that's time 0, we get to 50%, 1 half-life, 25%, then we get to 12.5%. So what we've done is we've reduced this down. Now it's only 12.5% of the activity it was initially because we've gone through 3 half-lives. Again, every single element has its own half-life, and so we've got lots of different things that some of them are found in nuclear reactors, some are not. Uranium-238 has a very long half-life. Something like polonium-214, very quick half-life, fraction of a second. And so uranium-235, that's one of the main components of a fuel rod, so it has a relatively long half-life, not as long as uranium-238. And again, that's part of the question of what do we do with those fuel rods when we're done with them? Because again, we don't use every single last bit of uranium that's in those fuel rods. And so when I've got something that's got a very long half-life, how long do I have to keep it sitting around before it's deemed safe to do anything with? I've also heard reports of them burying spent fuel rods. I read something once, I'm not sure about the accuracy of this, but I read something once that talked about postulating, could we launch these on spacecraft and leave them in space? I don't know. What do we do with them? That's, again, part of the problem. Okay. When we look at half-lives, again, we can look 0 half-lives, none's decayed, 100% is remaining. 1 half-life, 50% is decayed, 50% is remaining. 2 half-lives, now 75% has decayed and 25% is remaining. 3 half-lives, 87.5% is decayed and 12.5% is remaining. And then we just keep dividing in half from there. Okay, so we can do a couple examples here. All right. So if I have an isotope that's radioactive and I have a half-life of 20 minutes, how much of the sample will be left after 1 hour? So what I can do is, okay, I can have time percent sample. Okay, 1 hour is 60 minutes. So times 0, I have 100% of my sample. Okay, this is minutes. 20 minutes, that's 1 half-life. So I have 50% of my sample. Here, I'll also do number. So at time 0, I've done 0 half-lives. Okay, time 20 minutes, I've done 1 half-life. Let's do the next half-life, so 40 minutes. So now we're down to 25%, and we've done 2 half-lives. I can do 60, 3 half-lives. All right, so 12.5%. Okay. I could also look at 20 and 60. So 60 divided by 20 is 3. So I know I've undergone 3 half-lives. Okay. All right, here I have 75% of my sample has decayed after 6 hours. What is its half-life? So all right, so at 0 half-lives, 0% of my sample is decayed. After 1 half-life, 50% of my sample is decayed. After 2 half-lives, 75% of my sample is decayed, because I can also look at percent. Right? Okay, and so 2 half-lives. Okay, so 6 hours divided by 2 half-lives is going to give me 3 hours. So the half-life of this particular sample is 3 hours. Okay, and so that brings us back to that longevity of nuclear waste. We have long half-lives of these isotopes produced from these nuclear reactions, meaning that nuclear waste will emit radiation for thousands of years. Like I said, most nuclear waste is stored on site. They're trying to develop long-term storage options, so looking at doing things underground. But there's a lot of scientific concerns, like what happens if we bury this? What's going to happen to things underground? So that is the big concern. What do we do with this waste? Because when we look at radiation, okay, different types of radiation penetrate differently. Alpha particles, that doesn't need a whole lot of shielding. It gets stopped very, very readily. Beta particles, we need a little bit more shielding, so it can penetrate a little bit into our flesh. But gamma rays, these are high energy. They go very fast. And we actually need a chunk of lead to get those to stop. These two pass through our body. They can do a heck of a lot of damage. And so here I have a graphic. You can see alpha particles, they get stopped pretty easily. Beta penetrates a little bit, and gamma rays do pass through our body very, very readily. And so we get these, effects. If we have a little bit of radiation, not a whole lot happens. But as we increase the radiation, the damage increases. Our white blood cell count goes down even more. We start to see skin lesions. We start to see other physical effects. And then we start to see people die. And then the other thing too, this is just more immediate effects. But long-term effects of exposure is we do start to see, months, years down the line, people developing diseases like cancer. And so even smaller doses of radiation, lower than that 5.00 there, that'll cause death pretty dang quickly, we do still see radiation effects causing problems down the line when people are exposed to a significant amount of radiation that doesn't kill them initially. So these are things to be, consider. Nuclear power is a pretty good power option. It generates a ton of energy, does not cause all of the issues that fossil fuels do, but there are risks that we do have to consider, which is why we have reactors that are built usually pretty far away from where human civilization is. So like San Onofre, that one, if you drive up the 5, you'll eventually see it, but it's buffered by many miles on either side from where we have major cities in California. It's closer to where we've got some of the military bases and stuff, but to, our cities and our towns, San Onofre is pretty far away from those, so that way it's not right in the center. So if something does start to go wrong, there's more of a radius to contain it versus, right smack dab in the middle of a city. Okay, we'll look at some of these risks and what the future of nuclear power is coming up.